So here, in this proof, right? So as I mentioned little while back, the time why is the why is the proof generalized proof required? So the motivation here is that the generalized proof is required so that we can conserve computational computational resource, right? So that is why we are interested in proving that the square of an odd integer is odd, right? So that we can use this statement. We know that this statement is true. Using this statement we can make bigger calculations. Okay, without much ado, let's now jump into the proof, right? Okay. Now you see that we are trying to propose a generalized proof to this question, right? Okay. Now, what is the given? Given is an odd integer. Odd integer. Okay. Given is an odd integer. What we have to do, we need to square the odd integer, and we need to basically say or show that the square of this odd integer is also an odd integer. Okay. Okay, cool. Now uh, the given number is an odd integer. Well, I'm going to make a claim over here, right? So the claim is as follows. The claim is any odd integer any odd integer is of the form is of the form 2n plus 1. Okay, so this is a claim that I am making, and this claim is actually true because you take any odd integer from the entire number line, whatever possible odd integer you have. Every odd integer can be written in the form 2n plus 1, right? Just for the sake of like convincing ourselves that we are true, we can take, let's say, n is equal to 1. So if you substitute n is equal to 1, then 2n plus 1 will be 2 times n, that is 2 into 1 is 2, correct? Plus 1, that shall give us 3. Let's like take n is equal to 124, right? So that again, twice n plus 1, if we calculate that, so 2n will be 2 multiplied by 124, that is 248 plus 1, that is 249, correct? So we are finding that all the numbers of the form 2n plus 1 are odd numbers. So in this proof we are claiming that an odd integer is of the form 2n plus 1. Now, in order to continue with the proof, right? So whatever I'm writing in red here is just for you to like keep it in your mind, think in your mind. So this should go in the mind, right? Okay. In order to write this problem, we are given an odd integer to do square the odd integer, right? So we can write it as follows. We know that we know that an odd integer is of the form 2n plus 1. Okay, we know that an odd integer is of the form 2n plus 1. Then the square the square of the integer, right? What we'll do is we'll square this odd integer, just like the thing that I had done in this red ink above, right? So the square of this odd integer is, let's write twice n plus 1, in a bracket and put the square on top of that, right? I'm going to scroll it now. Okay, so you see 2n plus 1 whole square. It looks somewhat like a plus b whole squared, correct? And we know that a plus b whole squared is written as a squared plus twice ab, oops, twice ab plus b squared, isn't it? So, and also like, like by matching, by observation, you can see that a is nothing but twice n in this particular expression, in this particular binomial expansion, right? And b is same as 1. So this expansion, right, a square plus twice ab plus b square, in this, if we substitute a as equal to twice n, b as equal to 1, we will be getting the expansion of twice n plus 1 whole squared. So a squared is twice n whole squared plus 2 times a. What is a? A is twice n. What is b? B is 1. Plus b squared. What is b? B is 1. B squared, right? So a square plus 2 times a times b plus b squared. So this will give us 4n squared plus 4n plus 1, right? So we have got an expression of the square of the odd integer. Just imagine, like we had started with an odd integer 2n plus 1. We got that the square of odd integer is 4n squared plus 4n plus 1. You know what, we are just let's just see whether the derived formula is correct or not. So let's say that n is equal to 1, right? Well, or maybe not 1. 1 is very trivial. Let's say 3. N is equal to 3. So the odd integer will be 2n plus 1, which is 2 multiplied by 3 plus 1. 2 multiplied 3 is 2 ones are 2, 2 twos are 4, 2 threes are 6, 6 plus 1, 7. Okay, now the square is equal to 4n square plus 4n plus 1. So 4 times n is 3, correct? So in place of n, I'll write 3. On top of n, there is a small 2, that's a square, right? So square, 3 square plus 4 times 3 plus 1, which should give us, if you have a pen beside you, you can do it very easily. It should give you 49. 3 square is 9. 4 multiplied 9 is 36, right? 36 plus 4 multiplied 3 is 12. 36 plus 12 is 48 plus 1, that is 49. So you see, you can verify that this expression that you have obtained 4n square plus 4n plus 1 is the square of an odd integer of the form 2n plus 1 for all values of n. And maybe it is better that we restrict ourselves to positive integers, because the definition of a negative odd or a negative even is a little sketchy. Let's not go there. It will complicate things. So all positive odd integers are of the form 2n plus 1, where n should be 0 or more than 0. Again, an integer, right? So 0, if you put n is 0, we get 1. If you put n is equal to 1, you get 3. If you get n equal to 2, you'll get 5, and so on. So all positive odd integers are of the form 2n plus 1, and the squares of those positive odd integers are of the form 4n squared plus 4n plus 1. Okay, now why did we come here? And how is this going to help us? Remember, the statement, the direct proof, the statement that we need to prove using the direct proof method is the square of an odd integer is odd. So we have to prove somehow that this 4n squared plus 4n plus 1 is an odd number, right? We have to prove that this 4n squared plus 4n plus 1 is an odd number. Let me write that down. So we need to show that 4n squared plus 4n plus 1 is an odd integer, right? Now, see, let us not forget that in red, the claim that we had written. What was the claim? The claim is that any odd integer is of the form 2n plus 1. Now, this n can be anything, right? It can be a big number as 7,060,231. It can be like 9,999, right? But it's not a negative number. We have ruled out that case, right? It could be zero as well. So the n is a variable. So it's basically any odd integer would be of the type 2k plus 1 as well. It can be like 2 times this small cute house plus 1. This can also be the form of an odd integer, right? So what we will try to find out a number which multiplied by 2 plus 1 is our 4n squared plus 4n plus 1, right? So we can rewrite, we can rewrite this number as this number as follows. So 4n squared plus 4n plus 1. See, the plus 1, so the half job is done, right? Plus 1. Plus 1 is the half job. Now we need to write 2 times something plus 1. So the plus 1 job is done. We just need to now take 4n squared plus 4n and write that in such a way that it is 2 times something. Okay, let's try it out. So what I'll do is that I'll write plus 1 on the side, keep it aside. 4n squared. So can we take out a 2 from here? So can I write 4n squared as 2 into 2n squared? Cool, right? We can write 4n as 2 into 2n, isn't it? Now, because you see, like 2n square multiplied 2, the 2 and 2 gets multiplied and we get 4, and it is 4n square, exactly what is written in the previous line. And in the second line, the second term, we have written 2 multiplied 2n. So the 2 and 2 get multiplied and you get 4. And then there is an n after that. So that is exactly same as 4n. So what we'll do now is we'll take the 2 common from the first two terms, right? In the first two terms, you see the 2 and 2. There is a 2. There is a 2 in the first term. There is a 2 in the second term. So what we'll do is that we'll just take them out of and create a small bracket in which all the leftover terms will be added there, right? So what are the leftover terms? The first leftover term is 2n squared plus, there is a plus in between, right? So plus the other leftover term is 2n and plus 1, right? So see, now I think you agree with me that we have reached that position where we can say that like we have reached. I think now you can see that it is 2 multiplied something plus 1, right? So what we can say is that we can say let k is equal to 2n squared plus 2, right? Let k is equal to 2n squared plus 2. Then the square of 2n plus 1, which is the original odd number. This is the original odd integer that we started with, right? So the square of the original odd integer that we started with is 2k plus 1, right? And by the claim that we had written above, right? What was the claim? The claim is any odd integer is of the form 2n plus 1 or 2k plus 1 or 2 multiply house plus 1 or anything, right? So by that claim, by the claim above, this number is odd, right? Therefore, the square the square of an odd integer is odd, and that concludes our proof. Okay, can I get some thumbs ups on the chat if you have understood? Right, Pavitra, Santosh, Apu, Janani. Great. Abdul, Ramya, Janvi. Great. Okay, Naveen. Fantastic. So this is a direct proof. We are proving that the square of an odd integer is odd. Now, keeping this proof in mind, right? I would want you to go back after this class is over, after this lecture is over, and prove the following. Prove that the of square of an even number, even integer, let's say integer, is even, right? Okay, I'll give a small hint while solving this problem, right? The general form of even number is the general form. Can someone unmute and say, if you wish, you can say me. Form of even integer is, what should it be? Any guesses? Any guesses? No guesses? Okay, it's 2n. Just 2n. We don't need plus 1 here. Okay. Okay, so it's pretty straightforward. This is a much pretty straightforward problem. Okay, cool. Let's delve now directly into the rules of inference, and just as a small revision or something,
Yeah.
and we
Ritika,
can
Dhanush,
go
Ellama.
ahead and work on it. Okay, so rules of inference. It looks like as if it's a very big and profound thing. It's a very easy concept. Anyone can learn it, right? And again, anyone who can talk and think can understand this topic. So it's extremely easy. But again, don't get embarrassed if you do not understand. You can always ask me again. Okay, so what do we mean by inference? The word inference means to derive to derive conclusions to derive conclusion from premises premises. So this is a very technically loaded definition. So what are we saying? We are saying that there are a few premises. What are premises? Premises are basically some propositions. They can be simple propositions. They can be compound propositions, right? In logic, any statement is a proposition, right? The proposition is a statement that might either be true or it might be false, right? Depending on the situation, ground reality, or maybe sometimes when we have a compound proposition, the truth value of the compound proposition depends on the truth values of the simple propositions that make that compound proposition, right? Okay, so we have got some premises. Let's say, I'm just writing down the premise 1 dot 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 premise n, right? Let's say there are some n premises, right? I'll write capital N over here. Now, from these premises, what we do essentially is we take one premise and then we logically add them to the next premise, right? So add is conjunction, right? So we take one premise, we take the conjunction of that premise with the next premise, conjunction with the next premise, and so on. And this conjunction is is a commutative operation, right? So it doesn't matter whether we are taking the premise 1 in the beginning and premise 5 at the last, or maybe the premise 8 just after the premise 1. It doesn't matter, the order doesn't matter over here. It's commutative. So we'll take all these premises and we'll do this logical and operation, which is a conjunction, and that will help us in deriving the conclusion. Got it? So premise, that line is there, right? And below the line, therefore, this symbol here represents therefore. This symbol here represents therefore. We use this statement, this symbol, since middle school we have been using this symbol. So this is what an inference is. We are deriving the conclusion. This statement which we get at the last is called the conclusion. So we are deriving this conclusion from the premises. We are logically finding out the conjunction of so many premises, and we're getting the conclusion. Okay, now we have, okay, before moving on to identifying again the rules of the inference, um, so this so this particular structure over here, right? So premises and the conclusion, this together, all of this together is called an argument, right? It's called an argument. So what is an argument? Argument is premises and the conclusion, right? Premises and conclusion together is called an argument. Now, this argument can be of two types. It can be a valid argument or it can be an invalid argument. So we, like as human beings, like 21st century rulers of the universe, multiverse, whatever it is, we are like very intelligent people, right? So we do not want any argument to be invalid. So anyhow, let's identify when can we say that the argument is valid, when can we say the argument is invalid. So when the conclusion is true, we say that the argument is valid. So when the conclusion when the conclusion is true, when the conclusion is true, the truth value of the conclusion should be true, right? Then argument is valid. Then the argument is valid. So, so again, you see, what are we doing here? How are we getting to the conclusion? We are taking the premises and we are doing conjunction, right? And operation. In and operation,
Yes.
the result, if the result is
Dhanush,
true, then each of the premises have to be true, correct? So there is a run of
Dhanush
argument
Naidu.
here. There is a run of argument here.
Yes.
For the argument to be valid, see, again, there might have been a little disturbance down the line. So anyhow, what I'm trying to say here is as follows: an argument contains premises and conclusion. The premises combined by conjunction gives us the conclusion. Premises connected by conjunction gives the conclusion, right? Now, if the conclusion is true, then the argument is
Dhanush.
valid. If conclusion is true, then argument is
Yes.
valid. What does it mean? It means that for the argument to be valid, all premises all premises need to be true. And this is where, there is a, we can model more complicated situations. So there is a truth, there is another truth.
Diksha.
We are trying to connect these truths, and we will see whether like connecting these truths gives us like another truth, right? So if we have multiple truths, for example, um,
Divya,
okay, just a minute, just a minute. Okay, so exactly. So what are we saying is that there are n premises. Each of these premises have to be true, and only when all these premises are true, we will be able to derive a conclusion. Okay, so let's quickly get into the rules, get to know the rules of inference, right? And
oh
mm,
yeah.
yes, so let's get to know the rules of inference. So the first rule, right? This rule is called the modus ponens, right? Modus ponens. So this rule says that if we suppose we have a premise. What is a premise? Premise is it's a proposition. It can be a simple proposition. It can be a compound proposition. So let's say there is a proposition that P implies Q, right? So there is a
Sandhya
proposition
Chintamani.
which says that P implies Q. Okay, so now let's say that we have got another proposition. Which proposition? The proposition is P, right? Okay. Now, if we have both these are premises, right? So let's, we can also name them as P1 and P2, P1 and P2, right? So there are two
Oh yeah,
premises.
Divya.
So these premises, what we can do with these premises is as follows. We will conclude from these two premises Q, right? So let's say there is a statement that okay, in order to understand this, let's take a few statements P, Q, and R maybe. Yes, so let's say that we have got statements P, Q, and R as follows. Let's say we have got statements P, Q, R as follows. Hmm, let's say P is the statement, P is the proposition that it rains. This is a very favorite example of mine. Q says it is cold, right? Q is the proposition that it is cold. Okay. Um, so it rains, it is cold, Q, and maybe R is I need a jacket. Correct. So let's say these are three propositions we have. There are three propositions. So combining the first two propositions with an if then relation, right? So we get P1 as the first premise as if it rains, it is cold, right? The first statement means that the first premise means if it rains, it is cold. Correct. Now the second premise is just P, and P means it rains, right? So if it rains, it is cold. That's one rule, right? That's a proposition. That's a true statement. And the other true statement is that it rains. So definitely it is going to be cold, right? And that's exactly the statement Q here. You can see that, right? So that's why this rule is a very valid rule. This is a very valid argument. The P implies Q is true, P is true, therefore Q is true. Okay, let's move on to the next rule, that is modus tollens. Tollens, modus tollens.
Moda.
So this says that, let's say that P1 is a, is a premise as before itself. P implies Q. P2 is
Divya,
another premise which is same as negation of Q, right? So we have got two premises here. We have got one premise which is P implies Q, which means that if it, again, the interpretation goes as follows. Interpretation is, if it rains, it is cold, right? And the second premise says negation of Q. Q, the meaning of Q is it is cold. But the meaning of negation of
Queen.
Q is it is not cold, right? That's the meaning of negation of Q. The meaning of negation of Q is it is not cold. So what we do here is, according to the rule modus tollens, therefore the conclusion is negation of P. Okay. Now the meaning of the interpretation of negation of P matches with our example, right? In the example, we said that if it rains, it is cold. That is the truth, and it turns out that it is not cold. So it did not rain, right? It did not rain. Does it not make sense? If it makes sense, please, can you please give some thumbs ups? Okay, looks like they're pretty easy to understand as well. Again, we'll consider P as it rains, Q as it is cold, and the statement R as I need jacket. And we will move on to the next rule. So the next rule is as follows. Okay, the name of the next rule is the hypothetical syllogism. Syllogism, right? Okay. Now, let's say that we have got a premise. What is the premise? It is a proposition. Okay. The name premise comes because in an argument, we are deriving the conclusion from the premises using inference. So, the first premise says P implies Q. And the second premise says Q implies R, right? So we have got two statements here. Parallelly, as we have been doing over these last two rules, let's write down the interpretation of this according to the given example, given assumption. So P implies Q means if it rains, it is cold. Correct? P and Q. Okay. Now, Q implies R. It means if it is cold, I need a jacket, right? Q implies R. So Q is it is cold, R means I need jacket. So yes, what I've written is correct. Now, according to the rule hypothetical syllogism, the conclusion is P implies R. Okay. If you look at the right hand side, in the example, what is P? P is it rains. So if it rains, R would mean I need a jacket. I need a jacket. And you see that it makes sense. It makes 100% sense. It says that the first statement is if it rains, it is cold. Okay, fine. If it rains, it is cold. The second statement says that I do not know whether it is raining or not, but if it is cold, I need a jacket. Now, both of these statements are true. That means, I kind of, call up a friend at Delhi, and the friend says that if it rains, it is cold, right, in Delhi. And I call up another friend who is in the same locality in Delhi, and that friend tells me that if it is cold, I need a jacket. So I should, like sitting at Bangalore, I should make it in my mind that at Delhi, if it rains, I shall need a jacket. right? That's how our logic works, correct? So this is the rule of hypothetical syllogism. P implies Q, Q implies R, so therefore P implies R. Okay, okay, cool. Now let's move on to the next rule pretty quickly, right? We shall have a few more things to discuss after that. Okay, so rule number 4 is disjunctive syllogism. I should scroll my page a little bit more. Disjunctive, disjunctive, disjunctive syllogism. Okay, so this rule, oops, oops, syllogism. So this rule states as follows. So we'll take a proposition. In this case, we call them as we call these premises, right? So premise P1. We usually name these premises P1, P2, P3, and so on. So the first premise is P disjunction with Q, right? Again, so this is a different kind of a premise. It's a proposition. It's a compound proposition, but here we are more concerned about uh, if at least one of P and Q are true, this premise is a valid premise. Okay, because in disjunction, a disjunction is false if and only if both the simple propositions involved are false. Okay, and the second premise is a negation of P, right? So if logically, if you see, so here I will not use the previous example, right? It would become quite monotonous. So let's try to understand this with the principles of logic that we have learned previously, right? So in order for this rule, I have not yet written the conclusion, right? The conclusion, we'll write down the conclusion, but let's try to derive the conclusion, right? Okay, so in order for this particular rule to be valid, we need both the premises to be true, correct? Okay, now if P2 is true, if the premise P2 is true, then negation P is equal to true. And if negation P is equal to true, then P should be equal to false, right? Okay, now let's see, P is false, right? So we cannot have P as our conclusion because P is false. We need something in the conclusion which is true, right? Then only our argument is going to be a valid argument. So again, like if if uh, uh, actually, I should replace the word if by since. Okay, so since P2 is true, since now since P1 is true, then P disjunction Q is true, right? Because otherwise it is not a valid argument, right? So if P disjunction Q is true and P is false, then Q has to be true, right? Now Q is true, Q has to be true because P is false, and we know that false disjunction true is equivalent to true. We know this rule, correct? So if one of them is false, the other one has to definitely be true, and therefore the conclusion here is Q. Okay, so this is disjunctive syllogism. Okay, now there are some other rules, right? So the next few rules, I just state those rules, and maybe you can convince them or use them later in some way or the other. Okay, okay. The next one is addition. It's pretty simple. The addition rule is so let's say there is just one premise. This premise is P, right? Then the conclusion would be as follows. It will be P or Q, right? Where Q is any proposition, right? Or any premise. Q is not a premise, so Q should be a proposition. So Q is any proposition, because since P is true, it does not matter whether Q is true or false, right? So disjunction of a truth with another proposition, regardless of that proposition being true or false, is going to be true again. So this is the rule of addition. Then comes the rule of simplification. Well, this rule of simplification is also very easy. These are very easy rules, my students. Um, okay, the rule of simplification now. Here as well, like as the previous rule addition, there is just one premise. So in that context, it is similar. Okay, so this premise P1 is P and Q, right? This is the premise P and Q, P conjunction Q. So P conjunction Q, as we have been seeing throughout, that the premise has to be true, right? So P conjunction Q has to be true. So P conjunction Q is true if and only if and only if P is true and Q is true. So for P1, for the premise to be true, the conclusion should be P is true, or the rule of simplification can also help us in simplifying P and Q to derive just Q, right? Because see, simplification, the word simplification itself makes the idea clear. Here what are we doing here? Here we are having multiple propositions, P, Q, and so on, right? P can be a compound proposition, very long, so on and so forth. You have seen that in this module, right? And also Q can also similarly be another proposition, which is a compound one, and it can have like lot of other propositions inside it. So we are trying to simplify this. Now, if you see that there is an and between P and Q, right? So for this premise, this to be a premise, to be a part of a valid argument, it has to be true. So P and Q is true. So if P and Q is true, P has to be true and Q has to be true separately but together. They have to be simultaneously true, right? Therefore, the conclusion here would either be P or be Q. Equally, both are equally respected solutions. Okay, six is done. Seven, rule number seven. Rule number seven is conjunction. Again, this is exactly the definition of inference, right? You can tell, you can think of this as the definition of inference. There are two premises, P1 and P2. One of them is P, other one is Q. Then the conclusion will be P and Q, P conjunction Q. So this is exactly the definition. It's precisely the definition of inference. Okay, now we reach to the last rule of inference, and once we are done with the last rule of inference, we'll try to solve a problem, and you'll see that the problem is extremely easy to solve. Anyhow, this rule is called the resolution. Resolution. Okay, we will go back to our initial, we'll try to go back to our initial like example that we had started with, right? What was the initial example? The initial example was P means it rains, Q means it is cold, R means I need a jacket. So we will try to like use this example and understand this rule. Sounds good? Cool. Okay, so this in this rule we'll be having premise P1 and we'll be having another premise P2, and using these two premises there will be a conclusion, right? So this is basically the structure of all the rules, and whenever you go for any kind of like proof using rules of inference, this is the structure that you have. Okay, so the first premise goes as follows. The first premise is P or Q. From our example, let us write that down, what it means. I'll use the orange pen. I love this color. Okay, so this means that it rains or it is cold. Okay, it rains or it is cold. See the or, the word or, maybe I can write it down in some other color. What about magenta? Or it is cold. Cool. The second premise is as follows: negation P or R, right? And the interpretation of this in the physical realm, as we have defined, is it does not rain or it did not rain. Okay, it did not rain. It did not. Oof, I'll save some space here. Did not rain, and using magenta, I'll write or it did not rain, or I need a jacket. Okay. Now, if you look very carefully, in the example, let's first attack the example. Excuse me for that. Yeah, so what happens here, it we see that we are considering a statement: it rains or it is cold. The second statement says that it did not rain or I need a jacket. So somehow the statement the part of the statements, namely it rains and it didn't rain, are kind of uh, they become dysfunctional in imparting a meaning to the entire argument. So they kind of cancel each other in some sense, right? It rains or it is cold and it didn't rain or I need a jacket, so it rains and it didn't rain. So that brings it a lot of confusion into the scenario, and the truth value of that becomes false, right? So since that's a false statement, we ignore that, right? And then we consider the uh, the parts of the statement saying that it is cold, and the part of the statement that I need a jacket. And what comes as a conclusion here is it is cold. Oops, I'll make some space in the beginning. It is cold, or again, or in magenta, or I need a jacket. Therefore, it is cold or I need a jacket, right? So somehow what are we doing is that there is a conflict here. The conflict is between P and negation of P, and we're resolving that conflict using this rule of resolution by saying that, hey, you know what, there is P and there is negation P. So why don't you both of why the both of you not run just out of the window, right? Go take a walk. So the resolution, the conclusion in this resolution is Q or R. Okay, so these are the 8 rules. If you are on board with me on in understanding this entire thing, can I see some thumbs ups, or could not understand, could understand in the chat box, please? Sorry. Okay, thank you. Okay, fantastic. Now let's solve a particular problem. So this problem is very similar to maybe same to the problem that you kind of face in the exam, right? Okay. So this question says that there is a premise P1, which says P implies Q, right? And there is a premise P2 which says that, well, if P implies Q, then negation P implies R. Okay, and there is another premise P3 which says that, hey, you know what, R implies S. So it's as if, like, person 1, person 2, person 3 saying certain things, and you have to conclude something from what they're saying. Like, for example, you might have missed your lecture, your class, your day at college, university, or office, for a week or something, and then you meet your three different friends from who sits in three different parts of the class or three different departments, and then you meet together, and all of those three people start feeding you the stories, saying that, hey, you know what, this happened, that happened, hey, you know, that happened. And you have to, at the back of your mind, sit down and conclude that, okay, 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 so that is the thing which happened, right? So anywho, so here in this case, we need to prove that this is valid, right? So P1 is P implies Q, P2 is negation P implies R, P3 is R implies S. Therefore, negation of Q implies S. So this is what we have to prove. That is the conclusion we have to prove. Okay. Very quickly we are going to solve this problem because this problem is extremely easy to solve, right? Now, the way to solve the plan is as follows, right? So let's plan it out how to solve it. Now you see that in the statement to prove there is an S at the end. So we need to find a premise or a compound statement in which, let's see, S is there at the end, right? So you see that in P3, right, this is the premise where S is at last. And before S, Q is on the R is on the left, right? R is on left. And in the previous statement, in the premise P2, R is on right. So what that means is, the first step would be to use the hypothetical syllogism on P2 and P3, right? So by that, we can get a negation of P on the left and this on left, and an R on, no, not the R. The R is now out of the scenario. It's very good. S on right, correct. And then you notice that, in order to get, from the first kind of the from the first, what do I say, the premise, right? If we want a negation, see here, we have got R on the right, that is true, but we also need to eliminate the P negation P on the left. So if we can get a negation P on the right, that would be good. And you can see that you can find out the contrapositive of P1 will give negation P on right, correct? So the second step would be to take the contrapositive of uh, P1, and the third step would be basically to take the hypothetical syllogism of both above. So that's the crux of the plan, right? So we will, that's the, the sketch. So this is how we are going to solve this problem. So let's get into the solution, and quickly within the next 3 to 4 minutes we'll solve this problem. Okay, so this is how we write it down, right? So first, uh, consider the hypothetical syllogism of P2 and P3. Okay. Now, P2 is as follows. I don't need to give a colon over here. That's for full stuff is fine. P2, oops, P2 is negation P implies R. P3, oops, P3 is R implies S. Therefore, let's say that this conclusion is, see, we are going to use this conclusion as a premise in a next argument, next inference, correct? So let's name this as P4. Right now it is the conclusion, okay? Let put this in your mind that P4 right now in this case, it's just like the Schrodinger's cat, right? When you open it, in order to know whether the cat is dead or alive, you have to open the box and see. It's like quantum state, right? It can be in different states in different points of time. So similarly, this particular argument, with this particular proposition, negation P implies S, right now is the conclusion of this inference. Later, we are going to use this same proposition as a premise, right? That's why we are naming it P4. Okay. Next step is to take the contrapositive, right? Find the contrapositive. Contrapositive, I'm writing in the bottom of your screen, contrapositive of P1, right? Again, here let's just say that this is P5. The name, we are just naming it as P5. So what was P1 basically? P1 was P implies Q, right? Okay, P implies Q. So the contrapositive is negation of Q implies negation of P, right? And then we will again consider the hypothetical. Am I audible? Oops. Yeah, uh, I'm audible, right, guys? Yeah. I had not brought my charger to this room, so some security for some security purposes, my computer went to hibernate because I had said that, hey, you know what, when my computer charge is below this much percent, please put it on hibernation. Okay, okay, okay. So let's continue this and finish this off. I hope my screen is visible to everyone. Uh, am I not audible? Am I not audible? Can someone please confirm? Can someone please confirm? Okay, so what we do here is now, I am just, okay, looks like I am not audible. I will just look into some settings. What about now? Microphone is off. Oops. Ah, that is good. That is good. I think now it's all fine. Fantastic, fantastic. Okay, technology is our slave, right? So we can control technology as it is there. Anywho, so till now, sorry for the break in between. We have got three premises P1, P2, P3, and from the P2 and P3 we have considered the hypothetical syllogism as P4, which is negation P implies S, and the contrapositive of P1 as P5, right? So P5 would be negation of Q implies negation of P. Now again consider the hypothetical syllogism of P4 or maybe P5 and P4 and P4 as follows, right? So let's do the hypothetical syllogism of P5 and P4. So P5, let's write down the P5 first. So P5 is negation of q implies, right? Negation of q implies negation of p. And p4 says, what does p4 say? P4 is, look at the middle of the screen. It says that negation of p implies s. Negation of p implies s. And we are using hypothetical syllogism. So we will write the conclusion as negation of q implies s. Okay, so that's what our proof was about, right? So therefore we have proven that the given argument is valid, right? QED. Okay, so I think that's about it, right? So we started off with a direct proof. We wanted to prove that, an odd, the square of an odd integer is odd. Hmm? And why is a proof required, right? So this is a generalized proof. We're trying to generally say that you give me any odd integer, Mr. X, I am going to square it and I'm going to say that it is an X, it's an odd, right? And this kind of generalized proofs are important because we can conserve. I have written converts over here, right? So we can conserve. We can conserve our resources, computing resources. We can conserve our computation resource. It can be time, it can be space, whatever. But anywho, in this proof, we have claimed that an odd integer is of the form 2n plus 1, and we found out the square of 2n plus 1 as 4n square plus 4n plus 1, and then we rearranged the numbers, the terms, and we took k is equal to 2n plus 2n square plus 2 in the process, and we got it as 2k plus 1, and which is in the form of odd. And there is a little homework for you that you can prove that the square of an even integer is even, right? And I've given you a hint that the general form of an even integer is twice n. Then we got into the rules of inference. We observed that the definition of inference is given as derivation of a conclusion from premises, right? We have got a few premises and we combine them using conjunction, right? I think I should write that small commentary here as well. So we combine uh, premises using conjunction to get, oops, to get, to derive, right? Derive conclusion. Okay, so that's about the inference, the definition of inference. And this entire inference thing, right? The entire inference is called an argument. And an argument is valid when the conclusion is true. And since it's a conjunction which leads to a conclusion which is true, each of the premises should be true, right? And then we took an example, sometimes given a proof, sometimes does not given a proof at all, and we have identified the 8 rules um, uh, of of inference, right? And finally, we solved a problem at the end, and I think that's about it. Thank you.